So this is Miłosz Warzecha. Miłosz Warzecha is a C++ developer and a technology enthusiast who treats programming as a creative challenge. He often fails miserably, by the way, in that. That's what he admits. But he also enjoys the process of unraveling convoluted ideas into simple explanations. So he already was a part of Code Dive. It happened in 2017. An inspiring introduction to template metaprogramming was the thing that he presented right here. He said that he's not that stressed anymore because he's got already his own experience in being in public and talking openly to you. I hope he will have a really good time and you will have a really good time with him. C++, 20 coroutines once again, Asynchronity, or I don't know, maybe something else, Asynchronity, reimagined. Please give a warm applause to Miłosz Warzecha.
Okay, so hello everyone, my name is Miłosz Warzecha, and yes, what we're gonna be talking about today is C++ 20 coroutines. And so this is a brand new thing that we're getting in the new standard. There's been quite a lot of talks at this conference about this topic already, and it's worth saying right at the beginning that unfortunately this is not an easy feature to figure out. At least for me it really wasn't. And so what we've been given is really an amazing mechanism and a fantastic addition to the way that the C++ language operates. But there is a lot of stuff that is happening behind the scenes, and there is a lot of customization points which we have to take care of. And so that makes this feature a bit more difficult to get familiar with and a bit more difficult to figure out how it works. But with that being said, there is actually some real possibility that coroutines are going to change your code for the better, and so it's worth investing some time into understanding what is happening in here. And so what we'll try to do in this talk is to give some motivating examples as to why coroutines could be interesting to you, and also we'll try to analyze a bit of the inner mechanics and of the internal mechanism of what coroutines, what allows coroutines to work. So we are gonna go a bit through that, and then we also gonna try to get a little bit of a higher perspective of what coroutines can bring to building an application from a system design perspective. So that's something that we're gonna focus on a lot. And before we begin, there is actually some explanation necessary. Asynchronity is probably not a real thing. So that's the moment where I tried to be clever when thinking about the title of the presentation, and obviously it didn't work out. Asynchronicity is something that Google suggests. Asynchrony is apparently also something that exists, but yeah, asynchronity is not real. Sorry for that. With that being said, let's move on to some kind of brief introduction of what coroutines are and why they could be something that you're looking forward to. And so essentially, coroutines do not differ that much from a normal function. It's just they have this one little mechanism that gives them the advantage. And so we're able to suspend the coroutine and then transfer the execution back to the caller. And then we can resume back the coroutine and pick up the execution right where we left. And so what that allows us to do is it allows us to write an asynchronous piece of code in the same way that we would normally write a synchronous one. And this is really big for us. This is really big because what that in turn allows us to do is to introduce some kind of asynchronous solution into our application without relying on the overly verbose and overly complicated syntax, which usually accompanies these kinds of solutions. And so to illustrate that with an example, let's imagine we have some kind of synchronous program. So we have a function A, that function returns something, we expect it to return some kind of result. We then obtain this result, do something with it, and proceed with the rest of the program. So this is a very simple, harmonious and synchronous world when there is nothing scary, nothing complicated happening. And so at some point, we decide that we would like to make this application a bit more efficient. So maybe the function A is executing a little bit too long, maybe it's doing some input-output operations, and so we would like to launch it asynchronously. And what we could do and it's actually a pretty good idea, is to use toDasync. And so we changed the return type of the function to be std_future, and we use toDasync to launch a background thread and execute this function on this background thread. And then when we want to obtain the result of this function, we just call the .get method, and we're finished. We can go with the rest of the program. The problem with this particular solution that is visible on the slide is that it accomplishes nothing. And it accomplishes nothing because, unfortunately, the call to .get is a synchronous one, and so we're still gonna wait at exactly the same spot and for exactly the same reason. And the way to fix that, one of the ways to fix that is to use another toDasync and to introduce another thread. And so we now have possibly 3 separate threads, one that is executing function A, one that is waiting for its result and waiting to do something with that result, and the third one is our main thread, which is now free to do something meaningful and to do something productive, maybe. And so what happened here? We had some kind of performance issue. And we decided that we want to fix that performance problem with an asynchronous solution. And there are 2 things which might be an obstacle along the way. So first one is definitely that using this asynchronous solution might not even fix the problem itself, because there are some mechanics or some things which we are not aware of in our solution, and so the actual problem will not be that easy to solve in itself. But that can happen in any kind of programming challenge. The second thing that happens is that even if we do fix our performance issue, it's possible that we'll introduce another kind of problem into our application. And so we will fix the performance bottleneck, but we will probably introduce a structural bottleneck. And so what that means is that our application will be a lot more difficult to reason about. Our code will be a lot less readable than we would like it to be. And so fixing the performance issues is obviously very important to us, because performance is something that impacts the latency of our application or the throughput, for example. So it's something that we always will try to make the best of a kind, the best possible. But the structural bottlenecks is also something that we deeply care about, because that's in turn something that impacts the development process itself and how significant, how appropriate is our code quality. So it's also something that we very much care about. And so if you were to use coroutines to fix the performance problem and also do so asynchronously, it could look like this. And so we also changed the return type of the function, so it's not std_future, but we're now co-returning instead of returning. And also there is this co-wait keyword, which seems to be doing all the necessary job in here. And when we look at this code, it's clear that there is not much of a difference between this solution and the synchronous program that we had in the beginning. And so this is what we want. This is very good for us, because now we are able to fix our problems and introduce some kind of asynchronous functionality without the complications that were before. And so, yes, here is a brief summarization. So we're able to fix the performance issues using asynchronicity, and we do not have to rely on the overly complicated syntax that we usually have to deal with in other kind of solutions. And so what is this co-wait thing? It seems to be doing most of the necessary job in here, and so what allows us to work and what is necessary in order for it to work properly. So in an ideal world, you could probably go home after this conference and write a piece of code like this. So we have some kind of a function. You want to execute it asynchronously, and so now you have a new keyword for that. You have co-wait. And so we co-wait the result of that function, and hopefully this is going to take care of everything. And so the problem is that it's not going to work, at least not out of the box. And that's because the type of the function A in here that you co-wait has to satisfy certain requirements, or the type of the expression that you co-wait has to satisfy certain requirements. And that's because when the compiler sees co-wait, it's going to transform that into an entirely different piece of code. And that entirely different piece of code is going to need 3 functions which you need to implement in order for it to be actually functioning. And so those 3 functions would be await ready, await suspend, and await resume. And what happens is that the first thing that the compiler is going to call is await ready. And so this is the function that's going to be responsible for telling you whether or not the thing that you're looking for is already available to you. And so if it is, then await ready is going to return true. And then you're gonna go straight for that result. And that in turn means that you're gonna call await resume. So the third function that you can see in here. So that function is responsible for returning the result. And in that positive scenario that everything is already available, you just call wait ready, it returns true, then you call wait resume, and that in turn gives you the value that you were looking for. The other case, which is probably more likely to happen, is it's not the thing that you're looking for is not yet available, and so in that case, await ready is going to return false. And then the suspension mechanism is going to be triggered. And so the coroutine is going to be suspended, and await suspend is going to be called. Here you can customize what happens when the coroutine is suspended, and also here is the place what you would usually want to schedule the coroutine for later resumption. But you can also choose, in the simplest scenario, to just return the execution back to the caller, and then it will be your responsibility to resume that coroutine again. And so when you do that, the coroutine is going to be suspended, await suspend is going to be executed, and the control of the execution is going to go back to the thing that called the coroutine. And so now it's going to be your responsibility to resume it again. And so when you do that, the coroutine is either going to run to the next suspension point or just execute the whole coroutine body. And for example, at the end, you will return some value. Then await resume is going to be called, and that's going to return the value that you needed to the caller. And so there are 2 types awaitable types that's going to be available in the standard library in the C++20, which we're also going to briefly mention. And this is suspend never, suspend always. Their implementation is very straightforward. So wait suspend and wait resume functions are empty in both of the cases. The only difference is in the wait ready. And so in the case of suspend never, await ready returns true. And so that means that whatever you're looking for is already here, so there is no need to suspend. And in the case of suspend always, await ready returns false. So that means that what you're looking for is not yet available, so you should in fact suspend right now. And in a simplest scenario, using this functionality, it could look like this. So you have a coroutine, you call that coroutine, you print something before the suspension, and then you await suspend always. And so what then will happen is that you're going to suspend, you're going to return the execution back to the caller. Now it's going to be your responsibility to resume again, so we're going to do just that. There's going to be something printed out when we resumed, and then, for example, return a number or some integer of a kind. And we're also able to get this value and also print it out. And that's a very basic situation which could happen. But there are certain things on the previous slide which are not clear enough. And so there is this coroutine handle which await suspend is taken as an argument, and we don't know what that is. And also there is the suspension mechanism, and we're also not quite clear on what that's supposed to mean. And so let's try to take a closer look at those 2 things. And so in the case of a normal function, what happens usually is you need to allocate space for any temporaries or parameters or variables that function needs. And that means constructing a frame from that function. And in the case of a coroutine, the situation is very similar. And so you need to construct a coroutine frame that's going to contain the space for any temporaries or variables or some parameters. But it's also going to contain a space for the execution state that you need to restore when you resume the coroutine. And it's also going to contain space for the promise object. And the promise object is something that is your way to communicate with the rest of the world from the perspective of the coroutine. And so this is, for example, what's going to allow us to return a value from our coroutine. But here's the thing. In the case of a normal function, even if that function calls another and that one calls yet another one, they all have the strictly nested lifetimes. And so that's when this data structure called the stack is very useful for us, very efficient, and works in the best way. But in the case of a coroutine, the situation is a bit more complicated. And so if the compiler is smart enough to deduce that the lifetime of the coroutine is not going to escape from the lifetime of the thing that called the coroutine, then it is able to optimize. And so the coroutine frame is going to be allocated on the stack. But here's the thing. Coroutines themselves do not have a separate stack just for themselves. And so when coroutine frame is allocated on a stack, what that means is that it's going to live on the stack of the thing that called the coroutine. And so it's going to live on the caller's stack, and that's the optimized and more efficient scenario for us. In the other case, if the compiler is not able to figure that out, then a dynamic allocation on a heap will happen, because that's the case when the coroutine lifetime can possibly escape from the lifetime of the thing that called the coroutine. And so, because there is no 100% guaranteed scenario when this optimization will happen, you have to in fact expect that it can be present when you call the coroutine. What we've seen in the previous slide is that the suspension points themselves can be introduced using the co-await keyword. And so when a suspension is triggered, what happens is that any kind of values that were in the registers are going to be written to the coroutine frame. And also the point of suspension is going to be present in there, so we know where to pick up the execution when we resume eventually the coroutine. And that is also the moment when the compiler will create a coroutine handle for us. So this is something that the compiler is going to do. And what coroutine handle is essentially our way to communicate with that frame that we've just allocated. And so using the coroutine handle, we can resume the coroutine. We can also destroy it. We can check if the coroutine is done with the execution. And we can also get the promise object, which is, as we mentioned, is our way to return, for example, something from the coroutine. But the coroutine handle itself does not provide any kind of lifetime management, like a unique pointer or share pointer would do. It is essentially kind of like a row pointer, which knows where the coroutine frame is, but is not in any way responsible for managing its lifetime. Also, one bit of information which is going to be very useful for us a bit later on is that the coroutine handle can be default constructed, and so then it does not have any kind of coroutine frame associated with it, but it can also be constructed from the promise. And so the reason it's possible is that, as we've told, the promise is part of the coroutine frame itself, and so then the coroutine handle that takes in the promise is able to figure out what is the coroutine frame that it is now associated with it. And so that's going to be very useful later on. So that's what the coroutine handle is all about, and what in brief terms is the suspension mechanism involves. And so the only thing that is still missing, which we're also gonna go through, is this coroutine type, which is responsible for actually implementing what happens when the coroutine is called, when it is suspending. But here is the thing. We're gonna try to implement this type, but it is not, you should not try to remember each and every step along the way. If you really want to do that, then actually the compiler is gonna help you a bit. So if you want to implement this type yourself, the compiler is gonna complain that here is a method that I need and I don't have it, here is something that you're also missing. And this is not so that you remember each and everything, but so we have an overall vision of what is possible and what are the customization points involved in implementing a coroutine type. And so there are two things which were not necessary, which we are definitely going to need. And the first thing that we're going to need is the promise, as we mentioned. So this is our way to, for example, return something from the coroutine. So we're going to need that. And it has to be called promise type, exactly that. And the second thing that we're going to need is the coroutine handle. So those are the two things. The coroutine handle, in turn, is going to allow us to communicate with the coroutine frame. And so we'll be able to resume the coroutine to check if it's done, or we'll also be able to destroy it when necessary. And so as we've told, the promise is going to be our way to return something, so we need to have this value that we're returning inside the promise that we're implementing. And in our case, it's just an integer because if you remember on the slide, we're just returning or co-returning 42. And so the first thing that the compiler is going to complain about in this scenario is that it doesn't have the getReturn object method. And this method is fairly self-explanatory. So when you return from a coroutine, you return some kind of object. So you, for example, have the ability to call the .resume method when you want to resume the coroutine. Or when you want to get to the value, you also need an object to get to the value which is inside that object. And so the compiler is gonna, chronologically speaking, call that method right in the beginning. And it's also important to say that those methods that are going to be shown in here, you're not going to use them essentially. This is something from the compiler to generate some code, and so the coroutine is going to function in an appropriate way. And so the compiler is going to call that method and store that object. Is going to be stored as a local variable in the coroutine body, and this is what's going to be returned when you, for example, suspend the coroutine. And the way that we do that inside is that we're returning the coroutine type that is constructed from the promise. And the reason we are able to do that is because of this constructor which we already mentioned. And so we are able to explain to the coroutine handle what is this coroutine frame which it is now associated with by using the promise type. And so we are able to initialize it from a promise with a dedicated constructor just for this occasion. We can remove some of the boilerplate, so we're still in exactly the same spot. And so the two things next things which we are also gonna need is the initial suspend and the final suspend functions. And so those functions are also pretty straightforward. So when you execute the coroutine body, before you start executing any kind of statement from this body, you have the option to suspend initially, right at the beginning. And so this is, for example, if you want to have the coroutine ready for you, but you want to also be able to explicitly state when the coroutine is going to start executing, presumably at some later point in time, for example. In our case, in the initial suspend, we think that it's not really necessary to suspend, and so in that case, we just specify that it never suspends. And the final suspends, that's exactly the same thing, except at the other end, and so when you execute everything from the coroutine body, you have the option to suspend one last time. And so here we're also gonna just never suspend because probably nothing bad is gonna happen. Now the next step depends on what type of coroutine you try to build. And so if your coroutine is not supposed to return anything, then you're gonna implement the return void function. If on the other hand, like in our case, you want to return some values, then you will need to specify the return value function. This function is actually in itself not returning anything, so it takes an integer in our case as an argument, and it's storing the value that we want to return inside the promise that we have in our coroutine type. And so the only thing that is remaining for us is the unhandled exception function, and so here you can specify what happens if there is some kind of exception which you did not take care of, and in our case, we choose to just terminate the whole thing because it's fun, but you can pretty much think probably of something more clever. And the helper function that we're definitely gonna need is the resume function. So here we are just asking the coroutine handle to resume the coroutine for us, and we also have the get method, which works in a very similar way. So we ask the coroutine handle to give us the promise object, which is inside, and then we're able to obtain the value that we want to be returned. There is also some boilerplate necessary, so we allow for the default construction of the coroutine type, but we do not allow for any kind of copy construction of the coroutine. And the reason for that is that if the coroutine is done executing and we destroy the coroutine frame, which we've allocated previously, and there is a copy of it hanging around somewhere. And the coroutine handle inside that copy thinks that this coroutine frame is still valid, then we're gonna run into some pretty big trouble. And so we definitely want to avoid this kind of situation. And so we also have a destructor when we ask the coroutine handle to destroy the coroutine frame, and that's basically all the implementation that would be necessary under for this piece of code to compile. And so it is now compiling, and we will try to run this coroutine. And what will happen is that the return functionality will seem to be, well, not fully functional. It seems that we're returning not 42, but some random garbage from the memory, and we're not sure how is that supposed to mean anything. And the reason that happened is because of the final suspend implementation, which we briefly mentioned. And so there is a thing which you, in this case, just will have to remember in this little case. So the coroutine is destroyed either when you explicitly ask the coroutine handle to destroy the coroutine frame, so that's a clear scenario. But it is also destroyed when the final suspend resumed. And so whichever one of those scenarios happens first, that's going to trigger the destruction of the coroutine. And in our case, we've chosen a final suspend to just never suspend. And so when we want to get the value that we wanted to be returned, the value is already gone. There is nothing there. And so we need to specify suspend always in the final suspension point. But it's actually not the only case, but this could be very useful. Because if you suspend at the final suspension point, at the final suspend, it makes it also a little bit easier for the compiler to judge what is the lifetime of the coroutine. And so if you want to help this optimization case, for example, you want to make it a little bit easier for the compiler to judge whether or not the coroutine escapes or not from the lifetime of the thing that called it, then this is also a way, this is easier for the compiler to judge when the coroutine is being destructed. And so, does it actually work now? Yes, it seems that everything's fine now. That's PowerPoint compilation right there. So you can see that everything works fine right now. And so, from all of that, we definitely can see that there is a lot of customization points, and there is a lot of things that we have to take care of. And yes, they're also, because there are so many of them and there is so many mechanisms which we have a decision on, there is a large degree of flexibility which we have with coroutines. We also know now what is the coroutine handle, so we can communicate that way with the coroutine frame. We also have the promise, which is, for example, our way to return something from the coroutine. Then there is definitely this one thing that we have to remember, that the lifetime depends on whether or not we suspend at the final suspend of the coroutine. We're very quickly gonna go also through the yielding mechanism just to have the complete feature set of the coroutines. And so this is a little bit different from the returning from the coroutine, because returning is essentially a one-way ticket, and when you return from the coroutine, then it's done. In this case, you can yield a value, and you can do so repeatedly. And so that way you can generate even potentially infinite sequences, so you do not have to have any kind of upper boundary of what you're going to generate. And it's going to be useful, for example, for the lazy generation of some sequences, and it's usually called the generator type because of that. And very briefly, if you would want to implement this type, then instead of the return value, you would need the return void function, because we're not returning actually anything, we're yielding, and so the yield value function instead will need to be implemented. And here we're doing exactly the same thing, or very similar to what we've already seen. So we're storing the value that we want to be returned inside our promise, and then we're suspending. And that is the main way that the generator is going to be functioning. And so you yield a value, and then you immediately suspend execution. And when you suspend that execution, you are able to then resume it right away when you judge it appropriate. And so this is possibly the simplest scenario that you can have with a generator. So you're yielding some kind of values, and it's up to you how many times you're going to do that. It's up to you how many times you're going to compute the value and then get it in another kind of function. And so what's all this all about? Why would it, those mechanics, all those customization points, all those various functions which need to be implemented be necessary? Why would it be interesting to us? What is the perspective that would allow us to design an application with those coroutines and have that in mind that it should function in a more efficient way than what we've been already using? And so there is this concept called concurrency, and there is this concept called parallelism. And I personally used to think that those two are actually the same, or that those words can be used interchangeably, but that's definitely not the case. So those are, in fact, two distinctly different concepts. And the best way of thinking about it that I found is that concurrency is about structure and parallelism is about execution. And those are actually the words for Pike, who is, among various other things, one of the main designers of the Go programming language, which takes concurrency very seriously. And so what happens is that concurrency is, in fact, what enables parallelism to thrive in a given environment and to do its job properly. Parallelism, on the other hand, is something that is going to work the best if that concurrent structure of the application is in place. But if it isn't, if you did not take some time into actually investing into the structure, then it's going to pressure you into doing that, because otherwise it's not going to scale in the way that you would expect it to be. And so it's possible that it will actually slow things down instead of making it more efficient. And there is a very nice quote from Edward Lee, who said that if the next generation of programmers makes more intensive use of multithreading, then the next generation of computers will become nearly unusable. And to some extent, we can definitely identify with that, because it's very often the case that an application can run itself into the ground, doing even the most simple tasks, doing the most basic scenarios. And that especially can be the case if there is some kind of parallel execution involved inside. And so if those two concepts are actually different, then it should be possible to construct this kind of a matrix of what the different levels of concurrency and parallelism have as a consequence on the system that we're looking at. And so what should be the consequences of a given level of concurrency or parallelism on a given system that we're looking at. And so in a case of a system that is not concurrent and not parallel, usually what happens is the first scenario that we're looking at. And so we have the synchronous program. We're essentially just executing one task after another. So there is a lot of waiting, a lot of blocking probably involved. It's very simple, it's very straightforward. There is nothing scary happening here, but it's also probably not the most efficient case that we like to happen. And so there are two ways which we could go on about improving this kind of scenario. And so the first one that we could try is to create this concurrent structure inside this application. And so what that could mean is that we now have the ability to switch between tasks if we deem so necessary, if we think that that's going to be a lot more efficient. And so this is still the case that we only have a single executor. We still only have a single thread. But now we're able to speed things up. We are able to have a lot more efficient scenario because we have this ability to actually choose what we are now executing. The other case which we could go is to introduce more parallelism into our application. And so if this could be compared to sort of real life scenario, we could imagine that the previous one with the concurrency structure could be compared to a kitchen, for example. So you have only a single cook inside, but he has an appropriate structure, he knows what he's doing, and so overall the system works pretty great. It works pretty efficiently. But in this case, when you introduce more parallelism, you now have two cooks, except they don't know what they're doing. And so there is a lot of interruptions, there is a lot of conflict. One is using the resources that the other one would also like to use, or the other one is just going and throwing everything to the ground that the other one was doing and starts doing something else on top of that. And so this scenario can introduce some pretty problematic situations which we will have to take care of now. And it will not necessarily speed anything up. Instead, it can make things a bit slower. And you can probably see where I'm going with this. And so we have this final scenario when we have both the concurrent structure and the parallelism. And here is the world which we actually want to build. And so here, if we want, we can just execute one task after another if we think that that is going to be the most efficient way of executing. We're also able to switch between something. So if we want to eliminate blocking or waiting, we can switch to doing something else, and it's also going to provide us with a lot of efficiency in this kind of a system. And this is also the system where coroutines could be the best tool to try to build this kind of situation. So with coroutines, we are able to have this opportunity to switch between something and to suspend execution and resume it again at some later point in time. And so in this kind of world, we are able to build the concurrent structure of the application and then scale this concurrent structure with the parallelism that we will have at our disposal. And so this is probably the most efficient way about designing a system and trying to make it the most efficient. But there is one thing which is probably very problematic, and that is, what does this concurrent structure really mean? And how could we design a system that has this structure inside? So it's not like you just sprinkle concurrency on top of your application and it starts magically working. And the thing is that I admit there is not an easy answer that I've managed to find. And there is no step-by-step instruction which I was able to identify, unfortunately. But there are things which we could look at and which could provide us with some clues as to what should be the place to start of implementing this kind of solution. And so one of those two things could be looking at the shared mutable state in our application. This is usually something that is the source of our problems if we are doing something concurrently or in parallel. This is something that if we were able to eliminate, it would probably improve our situation a lot. But because we're usually dealing with a system that is more interesting, so this shared mutable state exists in our application probably for some kind of a reason. And so it's more clear that it will improve our situation, but it's not that easy and it's not that straightforward to actually try to remove it. The other case, and that is the encapsulation of the thing that try to mutate our system, is a bit less straightforward. But here is something that we could probably have some larger degree of flexibility in. And so usually when you have some kind of a system, there are certain parts of the system which should never be changed. So there are certain invariants which would hold no matter what true in this particular application. And so usually what happens is that it is up to you. It is your responsibility to remember, for example, that in this and this situation, this and this function should not be called. This and this change should not be performed, because changing a part of a system can always invalidate another part of a system if there was some kind of sharing involved, if that another part was also using some of the resources in these other parts of the system. And so because it is our responsibility, it is our responsibility to remember that it's usually very problematic for us. And so if we had some kind of way to encapsulate this potentially harmful logic, for example, inside a coroutine, then we could go about executing our application in a lot more elegant way. And so we could manipulate the suspension and resumption of the different coroutines while also having the potentially harmful changes encapsulated inside the coroutine. And this is very useful, especially in the case that we, for example, have the need to forcefully terminate something or cancel an operation that already is in progress. And so coroutines also have this ability to clean things up after what we've been doing, even if this thing was already executing for quite a lot of time. And so it's more clear, yes, that the shared mutable state is the culprit most of the time, and so avoiding that would be great, but it's usually not the case. And usually there is a lot of things that are just making the shared mutable state necessary in our application. But the thing about the encapsulation can be a lot more flexible, and here is where coroutines could help us a lot. So that's helpful because usually we're dealing with a system that is completely passive, and so we have some kind of resources, we're performing some kind of changes, we have the functions that we are relying on, and here in case of coroutines what could happen is that instead of having normal function, you now have kind of a function with a brain, which knows what it's doing and has some kind of logic encapsulated inside. And what's also worth saying is that it might actually be a bad idea, because we have enough problems with functions, and so functions with a brain could also introduce another set of problems which would be completely different and possibly even more difficult to handle. But it is an idea that seems very compelling, and it is an idea that would be certainly worth a try if we have the chance to do that with the coroutines. And so overall, what we could learn from all of this is that we are able to build this concurrent structure, and we can use coroutines as building blocks in making this concurrent structure available to us. And when we have this appropriate structure in place, then we can use this concurrent structure and scale it with the parallelism that we have at our disposal. And while also doing everything already mentioned, we're also able to introduce all of those functionalities, all of this asynchronous and multi-threaded execution, while still maintaining the readability and the quality of our code that we would like and we would desire. And so the one question that remains and that also needs to be asked is, can we just use a library for that? Because it all seems pretty much very complicated. And so from my knowledge, there is a couple. So there is definitely CPP Coro, there is also Facebook Foley, and from what I know, Louis Baker was heavily involved in all of those libraries. There is also a lot of resources, some kind of blog posts or CPP Con talks and every other conference. Also this conference, which has a lot of coroutine topics inside. There are articles from Louis Baker. There are articles from David Pilarski, who is also at this conference later as exactly this stage. And so there is a lot of opportunities to learn about the coroutines and to try to figure them out and what is exactly happening in here. And so this is certainly worth looking at, but from my side, this is everything. So thank you very much for your attention.
Big applause for Miłosz Warzecha. I wanted to say that this is a self-possessed slow fox of coroutines being right here in front of you today. He moves just like Frank Sinatra in slow motion today. So my congratulations and high five once again for your presentation. Please give a warm applause once again. Thank you very much. Okay, guys, so this is the best moment actually because I can see some speech bubbles over your heads, like chicken, hamburgers, like veggies, whatever you wish. But I think this is the right moment just to at least say thank you by asking a question. So if anyone willing to, I'm having a look all around, so feel free to come up to me and I'll just pass the mic on to you once again. Is it the moment? Hi, how are you? Good? What's your name?
Zbyszek.
Hello.
I have a question because I don't see any benefit of using coroutines. You haven't presented any difference between coroutines and async await, for instance.
So you do not see any difference, right?
I mean, to the good side, yeah. I mean, any benefits. So apart from that, I have to take care of parallelism because I need to take care if I can suspend, resume, and so on. So yeah, it's nothing done out of the box, nothing automatized.
That is true. Well, you want me to comment on that, I assume. So that is true that, yeah, we have essentially not a lot of things provided. We just have in the standard library, for example, the suspend always or suspend never. So that's definitely not enough to do something meaningful. So that's actually the assumption that for the time being, you're going to rely on some kind of library which is going to handle all the necessary works. So in the CPP core, for example, what you could use is this kind of single unit of asynchronous execution. What that could be is a task, and then you have this kind of functionally provided, which is not in the library, standard library itself. But when you have this functionally in place, there is some potential, I think, in here. So there is some potential even if you have only one thread and you want to speed things up and to make your application a bit more efficient. And there is some potential in a multi-threaded context. So there is a very nice interaction between coroutines and, for example, any kind of thread pool which you would like to introduce in your application. And so you can suspend a coroutine and then resume it immediately on another thread if you choose to do so. But yes, there is a lot of complexity inside, and so for the time being, you would have to rely on some kind of library. And if you cannot do that, then you have to implement all of this on yourself.
Okay, thank you.
Thank you very much for this question. Still anyone else willing to grab the microphone? Okay, so here's the source of questions. There we go. What's your name?
Jan. So thanks for the talk. And since we are implementing our own promise type, is it true that you could put a buffer in there and have like a channel in Go that you would, like, producer would produce values and
so you want to have some kind of Go routine equivalent in C++?
Yeah. Like you have a generator and it generates values, but could you generate them asynchronously? Like he would just push those values into
some kind of a buffer.
Yeah, the promise. Is it possible? Do you think it's possible with this kind of API design?
I think it should be possible, but at least that's not something that I've tried to tackle with. So it seems like something like definitely should be interesting, but it's hard for me to say definitely if that's gonna work. I'm not a compiler, unfortunately, but yeah, it's something that seems plausible.
Okay,
definitely.
Thank you very much.
Cheers, thank you. Okay, and here we go. Now to the right-hand side, at least my right-hand side. Hi, hello. What's your name?
Marek, hi. So I have two questions. One about, is there any move from the Boost community about doing their implementation, or maybe to take one of those libraries you presented to include into the Boost libraries? That's the first question. And the second, you've said that it is possible to resume coroutine from one thread in the second. Really? What about the stack in this?
Sorry, what was the second part?
A guy before me asked about, I know exactly what was the question, but you've said that it is possible to resume a coroutine post in one thread in another thread.
Well, yes, you can suspend the coroutine and then resume that same coroutine on another thread. That is possible.
But it will restart in the thread it was spawned, right?
No, it would actually just continue execution. I think that's something that I saw in the Microsoft case. They had a very interesting scenario where there was some kind of a function, and then you were co-waiting a very coroutine type which will take this coroutine, and so you were running your coroutine and one thread, and then you were suspending this coroutine and then immediately resuming this coroutine on another thread. So essentially you had one function, but it started execution on one thread, but then finished the execution on a completely different one.
Okay.
And when it comes to the first question, I don't know actually if there is a move from the Boss community to implement all of those things. Those are the stackless coroutines that we have in C++ itself. Boost has fibers, and Boost has the stackful equivalent of the coroutines. When it comes to the implementation of the things that we're dealing here, there is not a move that I am aware of, but maybe it's something that can happen in the future. Or maybe it already is, and I just don't know.
Big thanks for the question. Big thanks for the answer. There is still some room for the questions to be asked, so please feel free to come up to the microphone if you wish. I cannot see any movement at the moment. If so, then I want to say not only let's give a big thanks and big applause to Miłosz's, like stack of knowledge, but maybe let's give a big applause to his vocal cords as well, because he survived the whole hour. So please, do it. Let's do it again. Thank you very much.
Thank you.